now we are within the realm of the two-period durable good problem with two types. And we have already discussed the commitment. All right. So what we're going to do now is I'm going to give you, some of you were asking, well, we didn't see any proofs. I'm not going to give you the full proof, but I'm going to give you a full an overview of the revelation principle proof within this framework of two types. And then we're going to use the framework to write down the dynamic virtual surplus and so for the optimal mechanism in this simple setting. Okay, so in this two-period setting, the second period is special. It's not like an infinite horizon problem where we never know where the game ends. In the second period, because we know the game is going to end, which is a very restrictive assumption, of course, the seller has commitment, and because we derive the optimum under commitment, we know what the seller should do in the last period. So in the last period, we know that if the seller's posterior is low, is below this threshold mu bar, and remember this mu bar is this ratio of theta L over theta H. If the posterior is below mu bar, the optimal thing to do is to ask a price of low. And if the posterior is above mu bar, we're going to ask the high price. So now I'm writing, so the revenue when you charge the low price in the second period is equal to theta L, obviously, because you sell to both types and they make the revenue theta L. And if you post the price of theta H, the revenue is just mu times theta H because you only sell with probability mu. Now I'm going to write this in this. This is equal to this more interesting expression. The bottom line is the same. The top line is written a bit differently. What is the top line? When we sell to both types at price theta to both types, the seller is leaving rents to theta H because theta H is getting the good, but he's paying theta L. So he's paying rents at a price of mu2 delta theta H. So when theta L actually can be written equally as 1 minus mu2 theta L, that's the revenue we're making from the low type, who occurs with probability 1 minus mu2. And with probability mu2, we're facing the high type, and to him, we're leaving those rents. So this is actually an identity. And if we reorganize the identity, we get this expression. So now this is mu2 theta H times 1 minus mu2 theta L minus mu2 over 1 minus mu2 delta theta H. And this is what we call the virtual value of selling to theta L. Oh, thank you so much. So the stories that we didn't want to be late, and I wanted to get a nice tea. So that's why it's this. Not very professional. Okay, so this expression here is the virtual value of selling to the low type. So when we charge the low price, we are leaving rents, and this can be expressed in this equivalent way. So theta L is exactly equal to this expression, and I'm going to put it at the top of the line here. Now you're telling us, you can tell me why on earth do you go to all this trouble to express theta L in terms of this expression which involves rents? The reason I'm doing that is because now we're looking at the second period revenue of the seller from periods 2 perspective. When we go from the first period perspective, these rents that are being left to the high type, which are now calculated from the perspective of mu2, are going to be evaluated from the perspective of mu1. And now we will start to see this intertemporal conflict between the designer in first period with his prior and the designer in the second period. So here we are starting to see the time inconsistency problem. So actually limited commitment and This is an analogy we emphasize in our work with Laura on when we analyze this problem in an infinite horizon setting in a paper we published in T. We emphasize there that if we're thinking about equity commitment and we use our revelation principle to write down the problem of the seller, in the end, we end up writing a problem that resembles an intrapersonal game, where we have two types of, we have the incarnation of the seller today and the future incarnation of the seller. So there is an interpersonal conflict along the lines of Strauch equilibrium, if you know of these works, where, of like commitment problems to like good behavior, going to the gym, all of those types of more behavioral economics. All right, so that's why we're writing this expression. Now, as we were alluding to in the case of commitment, at mu2 equal mu bar, the virtual self, this expression is equal to 0, and the seller is indifferent between selling at price theta to both, or selling only at the high price and making revenue mu2 equal theta h, because that term is 0. All right, so that's another way to see the indifference. At mu2 equal mu bar, if you do this algebra, you're going to get that this term is 0. So you see that the seller is indifferent between both prices. So this is where you see how you see the expression. This is revenue as a function of the posterior period 2. At posterior below mu bar, the ultimate thing to do is to ask a low price, and that's the revenue. At posterior mu bar, the seller is indifferent between asking theta L or asking high price and getting it with probability mu bar. And then above that belief, it's better to ask price theta h and sell at mu. All right. So now let's start thinking about the input. Now think about limited commitment. What are going to be the first period messages? Suppose we have a mechanism where when the agent's type is theta, with probability P of theta, he reports mu1 in the mechanism. And with probability 1 minus P of theta, he reports mu2. And suppose that there are only 3 possible sequences of output messages and allocations resulting from these 2 different messages. Now, ultimately, all we care about is the total probability we see as S1, A1, S2, A2, S3, A3. That's all we care about. We don't care about these M's because they're not seen. So we can replicate the same distribution over final outcomes by generating a new mechanism which is equal to which gives us S2, A2 with probability P theta phi 1 given mu1 and 1 minus P theta phi 1 S2, A2 given mu2. So now we can call this new mechanism phi star, and the phi star input is theta. And now instead of having the agent randomize over these 2 messages, the agent is simply, if it was optimal for him to randomize in this way here, it's optimal for the agent of type theta to just report theta with probability 1. And this is essentially the argument in Besser and Strauch 2007, where they get the truth tellingness in this case where we don't observe the input messages. However, in the general framework, this requires some thought because the agent accumulates private information. And I have already given you a sketch of why we can get rid of the agent reporting the past messages. The reason I had given you before, I have actually given you, is that in period 10, the agent's private information is M1, M2, M3, blah, blah, blah. And I've already told you that we can replicate, if we have an equilibrium where the agent is conditioning on past input messages his behavior, we can replicate the same equilibrium with a public PBE, as I explained before. Do you want me to repeat the argument? But I explained why, because these messages, which are payoff irrelevant, are attached to the same public history. So the public history specifies the past payoffs, and because the agent is choosing things that will affect the future, they must be all optimal for theta to do that, and so theta must be indifferent. So we can construct a strategy that does not depend on the past messages. So basically, this reporting strategy at every period, we can just make it as a function of theta because it depends only on the public history and theta only. And then we can use a similar argument to this one to get to replicate play and have the agent just report type instead of reporting this pair of irrelevant messages. All right? That's sort of a the idea between the input messages. So now what about the output messages? So suppose we have, now we replace input messages with thetas, and now we have 3 different output messages. And suppose that there are 2 output messages attached to the same belief. And this output message is attached to a different belief. So in the durable good problem, we know what's going to happen as a function of the belief. There's going to be a price optimal given each of these posteriors. So the problem is simple because then we can just say, well, instead of having the output messages, I'm just going to equate the output with beliefs. And then I'm going to send each type now is mapped to either belief mu and belief mu prime, but I know belief mu is mapped to do different allocations. So first I will map a type to a belief, and then I can map a type and a belief to either A1 or A2 to replicate this part of the branch, or in this case, to just A3 to replicate this part. So now the probability that type theta induces mu is equal to these total probabilities. And notice that if the seller is seeing A1 and mu, he's updating to mu, and if he's seeing A2 and mu, he's also updating to mu. So the probability of A1 given theta and mu is, of course, by base rule given that. And we can write the same expression for the probability of A2 given theta and mu. And once you write these 2 expressions and you use some algebra, it's easy to see that the rate that this probability of A1 given theta given mu and the probability of A2 given theta given mu do not need to depend on theta once we condition on mu. So basically, a consequence of mu being literal means that once I condition on mu, I don't need to condition on theta anymore. And you can prove this by yourself. You write this expression also for A2, and you combine the ratios, you will see that you can cancel all the terms that depend on theta. So I don't want to do a lot of algebra on the slides now and spend like 3 minutes on this, but I'm sure you can convince yourself later. So the important thing now is that so basically we had this joint probability and we kind of broke it into A2 given theta comma mu times mu given theta. That's what we did here, basically. We broke this joint probability into the conditional. And then we use base rule to argue, which is like 2 lines of algebra, that this conditional probability now does not depend on theta anymore. So that's where we get the decomposition. So now our first transition probability is the beta. Sorry, I'm going the wrong way, is a beta. And our second transition probability is the allocation rule. That first, we map types to a distribution of our posteriors. So theta is mapped either to mu or to mu prime, which was the original thing happening. And then we map mu to a lottery over ultimate allocations. In this case, mu prime is mapped to with probability 1 to A3. And here we are mapping mu to either A1 or A2. Are you with me? This is the delicate part, and we're all after lunch. Maybe we have to do like something like mental push-ups now. So this is actually easy in the durable good because we have just the price following. In an infinite horizon game, we could have many other things happening that I'm not showing you on these pictures. For example, there could be many continuation equilibria, following a belief. So we would have to coordinate play, and that's the role of the correlating device. We could also have other crazy things happening. For example, if we go back, even to the input messages. Let me just go back to the input. So here, we took an indirect mechanism and we composed it with the reporting strategy of the buyer, and we got this direct mechanism phi star. It is possible that you get a blue mechanism composed with reporting strategy and a green mechanism composed with another reporting strategy, and they both give you phi star. In the original game, you had the blue mechanism being followed by different continuation play, then the whatever yellow mechanism, whatever I said, when we compose it. So you can have many different indirect mechanisms being summarized with the same mechanism that depends on theta. So then the play on the original game could have depended on this labeling of the mechanism. Also, the seller or the designer more general can be randomizing between mechanisms. So all of those things we have to deal with in the proof, and a lot of it is done with a lottery, which I'm not going to show you here because I think this is already enough complication for a talk. So all I want you to kind of remember at this point is that after we make the input theta, and the key argument there is to ensure that we can restrict attention to PDE, where the agent's strategy depends only on theta and the public histories, instead of mapping from the agent's private histories that are consistent with the given public history. Once we have that step, which is proposition 1 in the paper, then we easily can get the inputs to be types. And then once we have the inputs to be types, we see that, well, instead of having the output message being S, we can just call it the belief to S. And then there is some additional subtlety. What happens if we have a different continuation? If before, sorry, how do I go back? If there was a different continuation after S1 and after S2, despite the fact that both of these two messages are associated with the same beliefs. To do that, we use the public randomization device. So if there was a different continuation here, so the public randomization device will specify different continuation play here and a different here, and that way we can replicate the outcomes. All right, so after this, we show then that, hold on. So after that, we have that our output messages can be equal to beliefs. And as I said, in the general framework, we need to select between continuations. And that's where we're using the public randomization device in the proof. After we've done this step, you see how we separate the design of information, which happens here, from the design of the allocation, which happens in the next step. First, we draw the belief, and then we draw the allocation based on the belief. And that's, with this construction, we get this breaking of this joint transition probability into the beta, which is a mechanism's disclosure rule, and alpha, which is a mechanism's allocation rule. And that's basically an overview of the proof in a very simplistic way. Yes.
I'll ask you a question about of the equilibrium path
Yes.
history.
Yes.
So on the left-hand side, you have a mechanism and equilibrium.
Yes.
On the right-hand side, we have a equivalent canonical balance. The original mechanism and equilibrium may have off the equilibrium path history, but if you transform it into canonical one, am I correct that there is no off the equilibrium path in canonical? All branches, if you change theta, all paths are reached with a positive probability.
No.
So what's the off the equilibrium path in canonical mechanism in this particular example?
So first of all, some things. So if we start with a mechanism with arbitrary messages, blah blah, there could be sequences of output and allocations that are never realized.
Mm-hmm.
Never.
Mm-hmm.
Those we can prune.
Mm-hmm.
And then so
my impression was those things were completely, eliminated if you go from left to right. So
first of all, what we do is suppose we have. Okay, so for the A's, we're never eliminating the A's because the A's are always going to be observable, all right? For all the S's now, suppose we have all the S's can be broken into classes that are basically corresponding to beliefs if they're used on path. So for the S's that are never arising on path, we don't know what are the beliefs. So in the original space equilibrium we started with, we had some beliefs attached to them.
Yeah.
So all of those messages we can now.
I see.
We can use those. We can use the belief specification that was already in specification of the original assessment.
I see. Okay.
So if basically we had some messages that are never arising assigned to belief point 2, let's say if we have a big 2 types, the point 2 is we can keep that specification after point 2 even when we do this replication.
Okay.
And then of course if we have different continuations depending on those labels, that can be handled with a lottery.
Okay.
Yes, so this is actually easier than finding an equilibrium because our exercise is difficult because we work in an abstract setting, but what we do is we replicate. So it means when we take an assessment, the assessment has a full specification on whatever happens. And then we take the play as it is, and then we just break it into the categories I told you. There is enough path specification, and then we're going to keep that specification, and we're just going to be changing the labels where this thing arises. But there is a bit of subtlety because the point 2 can be a belief that was on path and could be something that was attached to some message I never saw. So we have to do it with some care. All right. So now how do we find the optimal mechanism? So now let's go back to our simple durable good 2-period problem. So the seller's problem has to maximize our mechanism revenue. Our mechanisms are M1 is taken to be theta, and S1 is taken to be distributions over theta. And then we have made this transition probability phi. We have broken into the disclosure and the allocation rule. And now we have the constraints of participation, truth telling, and then consistency between beliefs and output messages. And now we're going to use the same argument that we use with commitment. Because we have quasi-linearity and because we have separation between allocation and information, instead of writing down the mapping alpha as a mapping from mu's to distributions over q's and x's, so the mapping is a mapping from delta theta to a distribution over the allocations here, which is the Q is either a 0, 1 number or a real number. Here, instead of writing this object, we can use the same idea I was alluding to when we have commitment, and instead there we were writing Q of theta and X of theta, as you remember, right? We were writing the mechanism as of type. Now we are not conditioning on types, we're conditioning on posterior. So we're going to have a Q of mu2 and our X of mu2. And this is going to be the expected probability of trade at belief mu2 and the expected transfer at belief mu2. So here you have it written down. So no need to randomize over transfer. So X of mu2 is the expected payment when the output message is mu2. And Q of mu2 is the probability of selling the good when the output message is mu2. And now you start seeing the natural, how natural it is, because if we had a pooling contract in the first period, this mu2 is going to be the prior. If we had a fully separating contract, these mu2s will be Dirac measures on the types, like the direct mechanisms. And that's how you see that the direct mechanism is a special case of that, where mu2 is just the Dirac on the type, and we just don't write the Dirac, we just write theta. Okay, so now the seller's optimal problem becomes the following. We know that once we have a posterior in period 2, we know the revenue. This is the plot we had before. Do you remember the one? And when the mechanism spots out a posterior mu2, this is going to be the transfer in period 2. With probability 1 minus Q of mu2, we're not going to have trade because Q of mu2 is the probability of trade at mu2. Then we have some discounting and we move on to the second period. And the seller now, because the mechanism also has this beta that maps theta to mu2, has to the mechanism maximizes over beta, which are distributions over posteriors, and Q and X to maximize this expression. So mu2 is an element of delta theta, and then I have to choose this mapping. But notice now, that's the revenue in period 1. Okay, now that's what we have to maximize. And we have our constraints. Our first set of constraints is participation. So U star of mu2 given theta is the equilibrium utility of type theta when the posterior is mu2. That's the continuation. The first period payoff of the buyer is when the output belief is mu2, he gets theta times Q of mu2 minus X of mu2. When he reports theta, he induces a distribution over mu2. So this expectation now, when we sum over all mu2, and here I'm using finite sums just for simplicity. I don't want to write integrals. Obviously, if you have a continuum of messages, continuum of posteriors, all of these have to be more carefully written down. And then we also have truth telling, which means that the lottery over mu2s that I'm getting when I say the truth must be better than the lottery when I'm lying from mu2. So here, the report just enters the beta, and the beta is driving how often each mu2 arises, which determines the payoff today and the continuation payoff tomorrow. This is the truth telling. And then we also have the consistency, the Bayesian plausibility. Yes, please.
So what was the definition of mu1 and mu2?
Mu1 is the prior.
Prior.
And mu2 is the posterior that the mechanism induces. So
first expression, X of mu2.
So X of mu2 is the mechanism.
It's not multiplied by delta. So this must be the revenue in the first period.
In the first period.
And why it's a function of mu2 instead of mu1?
Yes, because it's a function of the posterior. We start with the prior, and the mechanism's output message is a posterior.
Oh, I see.
So the posterior, so basically the economics of it is the mechanism today is measurable with respect to the information it generates for tomorrow.
Mm-hmm.
Because every information I'm using today is going to be carried through forward tomorrow.
Mm.
So that's sort of what this result is getting us. And I think now that I'm going to go slower over this example, you will start to digest, hopefully, the food and this. I mean, we all have to. So the posterior enters the first period mechanism. So I'm using the information to design the allocation and the queue, and I'm carrying forward the information. And now this is the trade-off. If I want my mechanism today to be a very rich mechanism, I want to induce a lot of posteriors. The more posteriors I induce, the more constraints I have, because I'm going to have to deal with this seller or this person optimizing against different posteriors. So and then we have the base plausibility, which basically says that the mu of mu2 theta 2 is exactly given by Bayes' rule, which is, what is Bayes' rule? Is a probability that theta h induces mu2 times the prior that the prior probability of mu of theta h divided by the total probability that we are inducing mu2. This summation here is the total probability when we sum over all types of inducing mu2. So the probability, so if we divide that, and we are not dividing here because we want to make sure that we are writing this expression also for mu2s that never arise. So this is base consistency.
What was the definition of U star?
U star, I haven't written on the slide. I just told you informally. Yeah. It's the continuation base of the buyer at mu2. So for example, here, if mu2 is greater or equal, for example, to mu bar, the price is going to be P of mu2 is going to be equal to theta h, and this is going to be 0 for both types. And if mu2, so that then U star
I see.
of theta, mu2 is going to be 0 for all theta. And if mu2 is less than mu bar, yes, so then the P of mu2 is going to be equal to theta L. So then U star of theta L mu2 is 0, and U star of theta H mu2 is going to be delta VH, no, because it's going to be posted price, so it's going to accept it. So it's going to be delta dV, and this is for this posterior, and then for this we have that.
Okay.
Sorry, I did not put it on the slide, but it's good, right?
Mm-hmm.
So it's very easy here, but in general, yeah, it's a bit more, it's harder. All right, so now, but it's good to see this expression. So now we have these familiar expressions, and we only have two types. And because we have two types, we can do some simplifications. As usual, the seller will extract all surplus from the low valuation buyer, so the participation constraint will bind for theta L, and we're going to we can argue also that the high valuation buyer is going to be different between reporting theta H and theta L. So truth telling binds for theta H. And here we have two types. So in two periods. And because we have two periods, and actually, and this is also, we are thinking now about the participation and the truth telling constraint at the beginning of the first period. So now we don't have all these subtleties I was alluding to earlier with participation, with person. I'm starting to talk about participation and truth telling and indifferences, and we were talking about some subtleties. So this here now that we are talking about the writing the mechanism from the first period perspective, which is this problem, maximizes revenue subject to these constraints from the first period perspective. Now we can use the standard logic because we are now at the beginning of the game, and we can argue that the participation is going to bind without loss for the low type, and the truth telling is going to bind without loss for the high type. And after we replace these binding constraints, we can write the problem as in terms of virtual value. So now we are getting rid of the transfer x, and we're going to multiply Q of mu2 with the virtual value of selling to both types. And now you see this expression theta hat L I was using before, but evaluated at the prior rather than the posterior. With probability 1 of Q mu2, we continue to the second period. And now we have the continuation revenue written in terms of mu2, but evaluated from the perspective of mu1. And again, now we still have to do the expectation with respect to all the posteriors and mechanism induces. And sorry, let's go back slowly. So this step that we just did here looks kind of came out of nowhere. This is just a lot of algebra. As we usually have when we have mechanism design with transfers and nonlinear pricing, we start with a mechanism where we have to have the transfer rule and allocation probability, and we use the participation boundary constraints and the IC constraints to get rid of the transfers. So here we have to get rid of the excess of mu 2s. And once we get rid of the excess of mu 2s, in the exercise to do that, we use these expressions that Nietzsche asked me to write here, and because we're going to have a constraint where when we have theta L here and we set this equal to 0, of course, this is equal to 0. And this state there, we're going to have a theta L here. So that's going to tell us something about the x of mu 2s. And then when we have theta H here, we're going to have specific things for the mu 2s that leave some rents to theta H, and other implications for the mu 2s that don't leave rents to theta H. And after we do this algebra, we are getting rid of this guy here. But we have the deltas potentially, which are the terms I am going to be dumping in this part. All right? And now that's kind of all vanilla. Then we have this part that comes from the beta. We still have the same. So we just got rid of the x here. We still have this part we had before. We have the q's. And now we can do information design. Now we can say, whoa, look, this is the probability. If I forget, this is the probability that we are inducing mu 2. So instead of writing this mess, I can just write this as tau of mu 2, and then maximize by choosing tau, how often I induce each mu 2, and q. Are you with me? So now this is the seller's period 1 revenue from using our mechanisms which specify a distribution over posteriors. And as a function of posteriors, we have the beta, which became now a tau, like information design, and an allocation, as we usually do when we get rid of the transfers and write virtual surplus. So let me pause here for a second so you can take a look and tell me if you have any questions.
And you have a consistency question.
Of course. I should have first one more, and we have that. Yeah.
Is this a well-behaved constraint optimization problem that is more objective function? In what sense? Objective function, linear, and
everything is linear and everything is well behaved. So the spaces.
You have the tau times q, which is quadratic.
Yes, but let me show you how we're going to solve it.
So in the end, if things are discrete, this reduces to a linear programming, as in the one period case.
So what we do is we do the cheap thing. We say let's maximize belief by belief.
Oh, I see.
And then, so let me show you how we solve it. Okay, so now we're going to solve this problem. So first, let's look at the continuation. So this is why we did all this hard work. So remember before, we had this equality here of theta L. And I said we can write this as mu 2 theta H plus 1 minus mu 2 times theta L minus mu 2, 1 minus mu 2 of VH minus VL. Okay, something like this. And then this I called it theta L half of mu 2. Now in this expression, when we did this replacement of the transfers, we are getting mu 1 in there rather than mu 2 here. So now this rent is not evaluated when we are evaluating what happens when we sell to both types in period 2? When the posterior is high in period 2, we're going to sell only to the high type. So that's the revenue we're making from period 1 perspective. Because when we introduce the posterior mu2, we're going to be getting delta mu2 theta h. If we are paying rents now to the low type, from theta, from the perspective of period 1, that's the rent we are leaving. And that terms arises when we introduce the binding constraints. So how does this revenue look like? Remember, when we looked at R of 2 of mu2, there was a flat part here, and then the seller was indifferent between the low and the high price here, and then we were charging the high price. If we start with a prior mu1 less than mu2, actually, the seller from period 1 prefers the low price here rather than the high price at mu bar, because he's evaluating rents differently. And if the prior is high, actually at mu bar, so this is when the prior is above mu bar, the period 1 seller wants the second period seller to break ties in favor of the high price. So here this graph basically illustrates how period 1 seller perceives what happens in the second period. Yes.
So in the original explanation, the argument of theta hat L was mu2. And now the argument is, could you explain what you are doing here?
Yes, of course. So you see, this is this expression I'm putting here, and this expression this is basically what we got. This is the first step of this expression. This expression comes from the binding participation and truth telling. Sorry. So we have the binding participation and truth telling, and we have new one here, and we have this x2 that we're going to replace from this binding constraint and from the binding of the low type, the participation, and the binding of the high type. And when we replace this x2, the algebra, there's some algebra to do. It's like a few lines. It's not so trivial. I mean, it's algebra. It just like takes 5-6 lines and you get some expression. And that's where this expression comes from. This one.
And what about the argument?
And this one as well. There is a
that also comes from algebra.
Yes, the algebra.
Okay. Okay, I can believe you.
Yes. So this is not so difficult algebra to do.
There should be some intuition.
Yes, there is an intuition because you are evaluating the rents that you are leaving to the low type with the prior.
Yeah.
So that.
But theta hat is not a linear function of mu. So that's that puzzles me.
Oh yes, because we are grouping
mu
terms.
Divided by 1.
Well, let me explain. Let me show you some other thing that I should. Oh no, I'm going the wrong way. Wait a second. Let's go back even earlier. Let's go to the commitment, because that's where I had this expression. Sorry. Here.
Yeah.
So this theta L equals this. Okay, you agree with me? Now we're going to do algebra. Mu2 theta H minus mu2 delta theta H plus 1 minus mu2 theta L. And now I want to regroup the terms that have theta L here together. All right? But this term that has theta L is not multiplied by 1 minus mu2. All right? It's not. So when I multiply it with 1 minus mu2 to group it with this theta L, I divide. And that's how this gets theta L minus mu2, 1 minus mu2, delta theta H. And then I have I have a mu2 plus theta H here. So I do this algebra, if you believe me, is this. expression. So this is
Yeah,
an
yeah.
equality.
Yeah.
And then when
That's so
we do the participation and the constraints, we do similar kind of algebraic tricks to speed out these nice expressions. So they are not the most obvious things that comes out. So you need to work on it. But once you work on it, you get this expression that has this nice interpretation. All right, so let's go back. All right, so these expressions, so of course it's algebra, but even though it's just some algebraic manipulations, it gives us the ability to write this expression of revenue in terms of things that we're familiar with. Q times the virtual value of selling today to both types, because now when we have a posterior, we are not catering which type we're serving. We're saying this is a probability of selling at mu2. If we have a posterior that both types induce, we are selling to both types. And this is the continuation. And then, as I said, we replace the beta with the distribution. And now we're about to solve. Okay, this is where we were. Sorry. I know some people get dizzy with all this back and forth. So now we have to take a deep breath, because now actually the solution is going to be simple. I'm going to show you the solution with graphs. So if you buy this algebra, which indeed takes some work to do, I believe there are more interesting things to show you than this algebra, so we will skip it. And we will show you how to solve it. The second period revenue is this one. We see the disagreement between the second period seller is always indifferent at mu2 equal the bar. When we're looking at the first period seller, we see the prior is low, the seller prefers the low price, clearly, because theta hat at mu1 is above this. And when the prior is high, the first period seller wants actually the high price rather than the low price. This is the case where we know that we don't have problems with the immediate commitment, because we said that when the prior is low, we're just going to ask the low price, everybody's going to accept, and we are going to go home. That's the easy case. The hard case is when the prior is high and we want to ask the high price, and the commitment solution says ask theta H, theta H, theta H. So because this is easy and we're done it, we're going to focus on this case. So now let's maximize this expression for this case, for the prior that is high and we have this disagreement. Now let's look at step one. Suppose, now I'm going to try to solve the problem that Michi wanted me to solve. And we're going to look at the inside problem, and the inside problem is linear in the Q. So for each mu2, I'm going to maximize. One thing I can do is for that mu2 as a delay trade. So if I delay trade, I multiply the first term by 0, so that it disappears, and then I put probability 1 in the second term. Or we can just flip it. Choose to trade always and assign 0 to no trade. Then we are going to get the blue. So now I'm showing you the revenue as a function of mu2 from always selling versus always delaying. Of course, you're smart. You can say, why do I choose either the blue or the blue or the black? We can actually optimize. When the black is above the blue, we do the black. And when the blue is above the black, we do the blue. So for the mu2s, that this is above the value of selling today is above the value of delay, we are selling. And for the beliefs where the value of delaying, the black thing, is above the value of selling, we do the same. So we replace this with the max. And now, no more Q. Done. Now we do Cavendish against curve. Now we have an objective. This is a one with two types. This is just one number. And we can concavify. So if we start with a prior here, we can split it in two. A posterior at mu bar, where the price is going to be high, and a posterior at 1, where we're going to sell with probability 1. So now you see that we get this kind of Bayesian persuasion field, which is a consequence of equating the output messages with beliefs. And this is basically turns the problem to constrained information design. And we have a constrained information design because we just don't have Bayes plausibility. Only we have that the beliefs have to satisfy participation and truth telling, which are already fed into these expressions. So that's basically how we can solve it. You see that once we have once we turn this beta into distribution over posteriors, then we can solve at least this problem by choosing the Q posterior by posterior, pointwise, because the expression is linear. And then once we've done that, we just do information design. If we have a continuum of types, as we're discussing on our way to lunch, this is much harder because now the mu2 is a whole function. And we,
I see.
and now you have to design the distribution over these functions. And as I was saying also before, the tools what we have by, let's say, Sforzak and Martini and Ariel Bobichenko, I think Yamashita and someone else have a paper in TE about that do the bipooling and these techniques. All of those techniques, they think about settings where if we have a continuum of types where the posterior mean is fully determining the payoffs of everything. And if we have that, we can solve the problem. And actually the application I'm going to show you in a minute has this property. And that's how we can solve it. All right. So we can do the same revelation principle. So in the main part of the paper, we prove the revelation principle for a finite type space. And we also have an extension to in the econometric version of the paper, we have a continuum of types. But when we have a mechanism selection for a continuum of types, the extensive form game is not well defined because so we have these problems identified by Ullmann's work, where he basically uses, and then there are subsequently people write down these behavioral strategies where, so the distributional strategy approach by Milgram and Weber. Here we have even harder issues to deal with. So to give you a nutshell, so the revelation principle that I gave you holds verbatim for a continuum of types. It's just that for us to prove it game theoretically, we have to use a novel framework to capture the extensive form without running into difficult measure theory difficulties. The issue is the histories. You remember you were asking about the histories? In our mechanism selection game, because the histories feature mechanisms, to make the principal and the agent's payoff measurable with respect to histories, we need an appropriate sigma algebra on the space of mechanisms. But when we are composing mechanisms to prove, to do like revelation principal arguments, the sigma algebra that would work and make things measurable may not work for the composition of the mechanisms. So basically, it becomes measure theoretically close to impossible. Or we've talked to many people like Max Tinchcoming, who's my colleague, who knows all this about non-standard analysis. So we found a way around it by developing a semi-game theoretic framework that sidesteps the issues by still retaining the strategic features. So I don't have time to, either you have the slides, and the slides have an appendix explaining the approach. The important thing for practical purposes is that the revelation principle applies verbatim, and actually the application I'm going to show you is involving a continuum of types. All right? So it's just that some of the issues may be, for most applied economists, might be just, theoretical footnotes. When we think about defining expectations, we need to be correct, that we have measurability, so that's all. In any case, so now let's think about an application with a continuum of types. Yes.
I vaguely remember that Fiorelli has a paper on how to define sequential equilibrium in this kind of, continuum types, if I remember correctly. Is this something related to what you are talking about here, or
No,
no? Okay.
I mean, it is related that it's a difficult math.
Okay.
I mean,
Okay.
okay, strictly speaking,
Uh-huh.
we don't have sequential equilibrium solved games that have a continuum of types.
Mhm.
We usually write BB. So here we also use BB. We don't use sequential equilibrium because sequential equilibrium is hard to define.
Mhm.
The notion of sequential equilibrium developed by Phil and Roger is we're not using sequential equilibrium here, and there are some subtle issues there, and they have to define nets, so not like not sequences, like more complicated notions to define the sequence of the notion of sequence.
Mhm.
And it's not really related. The issue here comes from the fact that we want measurability with respect to histories, and the histories have mechanisms inside which are functions. Okay, so we're going to be thinking about a paper we published in RAND, where we're thinking about applying this technology to thinking about a firm using the purchase history as a tool to do price discrimination. So there is a there's also some practical motivation of this, and maybe I want to show you here that all the hard work we do to get some theoretical results as theories, can be used to ask some questions that could be of practical relevance. Consumer, for example, we know that consumers' purchase history is available to firms, and Gmail tracks purchase histories, and there's also some instructions of how to delete it. If you press the link on the slides, there's this. If you press a hyperlink on the slides, you will show you how to delete your purchase history, and which can be used for price discrimination. Of course, that's how Gmail makes money. I mean, Gmail is free, but everything that's free is more dangerous. We know how Amazon makes money, at least in some ways, but Gmail gives you this nice email for free. Well, they make money somehow. So Priceline personalizes search result based on users' history and clicks, whatever. So we know all of those things. So the availability of the consumer data facilitates price discrimination, and actually it's the endogenous availability of data that is gleaned from past interactions. So there are two ways in which consumer data is endogenous. It's endogenous because given the choice set offered by another firm, the consumer trade-off, better match versus price discrimination, if we're thinking about very sophisticated consumers. And actually nowadays, we have written all these models in the past, and everybody was very rational. So we were thinking, the consumer anticipates that they're going to be, discriminated. But if you talk to more applied consumers, they say, nobody really thinks about these things. But nowadays, we're going to have our bots or our agents doing things for us in a few years. And actually, those bots might be more strategic than us, and they might be able to think, okay, well, if I behave this way, then the firm is going to know that. So now I think we're even getting closer to the standard realm of game theory, because a lot of people are going to be behaving through agents. So the data is endogenous given the choices of the consumer, but also something, this is new in this kind of work that we did with Laura, that the choice set of the consumer that the consumer chooses from is chosen by a firm. So if I give you a very coarse menu, there is no way to reveal yourself. If I give you a very fine menu, if you want to, you can reveal yourself. But I could even prevent you from revealing yourself if I want to. And there is a bit of a discussion, even in by the White House or other regulatory bodies, that, well, it's nice to have consumer cookies and data, because then we can use this data to personalize goods and customize goods. So this has been put forward as an argument. Well, all this data is useful because we can actually provide niche products and richer varieties. And now we're trying to say, well, is that true? Are we going to get more varieties or less varieties? And actually, we're going to see that if we're thinking about this data being used for further discrimination, eventually it's going to lead to less varieties. This is basically this. However, the richness of the firm's product line determines the richness of the data available to the consumer, to itself, to the firms itself, and to other firms, which in turn determines the possibilities to price discrimination in the future. And the question is, how does the threat of downstream price discrimination, of limited commitment, basically, shape the upstream design of the product line? So I don't want to bore you with all this literature. I just want to say that there's a big literature in IO about price discrimination based on past history, but here we're not just thinking about pricing, we're thinking about how the availability of products changes. And there is some work by Bergeman, Hoyman, Morris, I think forthcoming JPE, where they are thinking about flexible information designing Moose and Rosen. Compared to that, the application I'm going to show you has endogenous data set, and we're going to be using the revelation principle we just discussed, but also we're going to be thinking about the extension of that result to settings without fully persistent types. All right, so this is a problem we're going to be looking at. So I'm going to look at a two-period problem, and we're going to have an upstream firm who chooses a quality rate, and this is. So the reason I'm going to do this application here with you is that I chose to do it for two reasons. First, the first period type is a continuum, which is something different. The second period information is not fully persistent, and it's binary. So your type in the second period is your value about another good, which is correlated with your type in the upstream period, but it's not continuous. So we are going to be able to deal with the posterior issues about this object. And we are also showing you that the framework can be used to study situations with not fully persistent types, and that, and solve problems that are not that of trivial, like the one we did with the two types, okay? So the upstream firm chooses a quality range on a non-decreasing marginal cost. So it chooses a quality range from 0 to Q bar. There is a price of quality, the cost, and next one is the period one payment from the consumer to the firm. The consumer of type theta has utility theta Q1 minus X1. Theta is distributed according to F, that has some positive density, and we're going to assume that the F satisfies a monotone hazard rate. Now the downstream firm produces an indivisible good 0 at marginal cost, 0, and so the downstream firm produces a good, and you can either sell the good or not sell the good, and there is a transfer. And the consumer has a value, a low or a high value, and utility V of Q times minus X2. So a consumer, so think about theta as being your value for a vehicle. So you have a vehicle, there are a continuum of types for the car, and then the second period firm sells you a maintenance plan. So the maintenance plan, you either have a low value for the plan or a high value for the plan. So the upstream firm is the car manufacturer, and the downstream firm is someone selling you the maintenance plan, which can be sold by the car manufacturer itself. Like sometimes Honda will say, do you want Honda Care? I think in the US. Honda is a Japanese firm, so it's a good example here. Although I saw the cars look different here. In any case, so let's go back to this. So you're Honda, you're selling theta cars, and you're selling maintenance. So the maintenance, you either buy the maintenance or not buy the maintenance. There are many qualities of Hondas. You can buy with ABS, with, whatever. So every model comes at many different Qs. So the question is, what many versions of the model you're getting at the upstream, how many versions I'm designing, and then the maintenance plan is more vanilla. You either get it or not get it. And the value for the maintenance plan is correlated with your theta. So a consumer of type theta has value VH with probability P of theta, which is equal to F1 of theta. So this is a parametric assumption here, of course, that we're making. the important thing is that the consumer's private information is not fully persistent, and we can rely on results of a paper an extension of our result with Laura we published in the European Economic Review a few years ago. There was a volume for our dear colleague Conrad Weirdoff, who passed away too young, unfortunately. In any case, so this is a version of the paper this is the version of the result we're going to be relying on today. So applying those results to the upstream problem, without loss of generality, the upstream firm will offer a direct Blackwell mechanism, which is going to be a disclosure rule and an allocation rule now that's going to be a posterior to a distribution over menus of qualities and transfers. So the upstream problem is basically Musa-Rosen problem, and the downstream is a vanilla durable good problem like the one we just solved.
So what can the second period upstream firm observe about what happened?
The quality of the car you bought and the output, the quality and the belief. So we are going to assume, so actually we're going to make different assumptions depending on whether the firm is vertically integrated, whether they are selling the data. We have different versions we've analyzed. And but in the main problem, if it is a vertically integrated firm, so it's the same from Honda selling you the car and the maintenance, they've seen Q and they've seen the belief, because they use the belief to sell you the Q, the quality and the charge, and then they know the posterior, and then using this data, they can actually assess how likely is you are the low type or the high type. So the information design here, we're mapping types to distribution over posteriors. And here the product line essentially is going to be reflected in the disclosure rule, because the coarser the beta, the coarser the product line, and the less downstream discrimination. And there are upstream, we have two goods. Variable quality and consumer information. And the direct Blackwell mechanism will encode how consumer choices translate into downstream beliefs. So the upstream firm basically not only provides, provides qualities, but it also generates this data that can be passed on to the downstream firm. All right, so now we're going to make a bunch of assumptions so we can solve this problem. And of course, we tried to solve it with more general specifications. We could not. So we are going to make a specific assumption about the cost. This is quadratic cost, and this P of theta equals F1 of theta. And the second assumption is that F1 is uniform. The reason we're going to make this strong assumption, and I mean, is that under this assumption, it turns out, and under these two assumptions, it turns out that the mean of the posterior matters only for the second period, and then we can use the non-design techniques, information design techniques to solve it. So that is just this is the only basically what we did with Laurie is we said, okay, this is a very nice problem. It's very natural, I think you believe me. Like, what happens? You have Musa-Rosen followed by some downstream. And then we looked at the information design literature and said, what is the state of the art there? What is the best results we have to solve? And the best results we have are ones only that depend on the posterior mean. So then we had to cook up with some specification that will lead to information design tools that allow us to solve the problem. Basically, we backward engineer the specification so we can solve it. But at least a lot of the economics we get are general, because we're going to see a lot of distortions that arise. And because we have the specifications that is solvable, we can actually see exactly how the distortion of limited commitment is shaping the menu. All right. So we're going to be thinking about different scenarios. You can think about the upstream profits being the product line profits like Musa-Rosen plus gamma times downstream profits. So we can think about two scenarios, vertical integration. So we have commitment basically. So vertical contracts, the upstream firm chooses a product line and downstream allocation. So this is a dynamic mechanism design problem. This is not even so vanilla. I mean, this is used like Toyka, Pavan, Seagull techniques. This is basically Pavan and what's his name? Who used to be in Toulouse and now he's at Essex.
He was Essex.
The guy, the Australian guy.
Northwestern guy, right? You know.
Yeah. What's his name? Oh, I'm liking. He's from Australia.
Yeah, Garretto.
Yes, Daniel Garrett and Alessandro
Yes.
Pavan have a series of like dynamic mechanism design problems with full commitment. So the vertical integration here, which is the full commitment, is going to be the benchmark. So still, this is, not like the stand. Yeah. So we're going to have under vertical integration, which we call the full commitment, the upstream firm chooses product line and the downstream allocation. And then we have the second case is non-contractable contractable downstream action. So there we have separate firms or limited commitment. So the upstream firm chooses a product line, and then observing the purchase good, the downstream firm chooses prices. So the main result we're going to see is that product lines are distorted above and beyond what the efficiency rent trade-off dictates. So we're going to get in beyond the second best. So we have the first best, but when the firm knew the type, we have the second best. This is sort of the Lafont-Tirol characterizations with the constraints. And now the third best we're going to get will also reflect the limited commitment impact on that. Yes.
Question. So the upstream firm's profit is a function of gamma. What's the interpretation of gamma?
Or it could be the fraction of downstream. I can maybe charge you a commission based on the profit you're making, sort of. Or we are splitting the profits. If gamma equals 1, it means that I am the same firm. If gamma equals 0, it's a separate firm. So I don't care about that.
So in the case of vertical integration,
It's going to be gamma equal 1 and full commitment.
without any discounted, gamma is equal to 1.
Yes, or you could think about it as this.
With vertical integration with discounting, gamma is equal to delta.
Yes, and then you can also think about how much you care about.
Partially, your downstream firm is partially owned by the upstream firm.
Yes.
Then it's a fraction times.
Yes, you can fraction.
Okay.
Or you can think of a weighted sum, you can think of gamma, whatever, and then
Yeah.
They can have, in the paper we discuss different interpretations about this gamma. It could be 0, it could be 1, it could be in the middle. Yes. Where am I? So I got lost. Okay, so I have like 15 minutes. So maybe I want to choose, or maybe I can take a few long. I have, how long, when do I end? 2:45?
Yeah, 15.
Okay, good. That's enough. I mean, all right. So the period 2 problem, we know it because it's the same thing as the durable good problem. It's going to be 2. We have low or high values. The firms believe about theta is F2. So now we just use different notation. B bar is a probability. B bar is the mu bar that we had before. Sorry for the change of notation. I follow the notation of the paper. So P bar is like the mu bar we had before. So it's a probability that the firm has high value. So, actually now I'll have mu bar here, sorry. Oh no, it's okay. I said, I call this a variable. So if this belief is equal to mu bar, we're going to sell at V. If it's below, we're going to sell at VL. If it's above, we're going to sell at VH. That's what happens in the second period, like before. And we have the indifference. And now, so the downstream pricing determines the rents a consumer of type theta expects in the second period. So this is the rent if the price is low. If the price is high, the rents are 0. And so if the downstream firm assigns sufficiently high probability to the consumer being high type, the consumer gets nothing in period 2. And the downstream optimal pricing under absence of consumer data plays a role. So the prior mean is a half. So what happens at the prior mean? At the prior mean, when mu bar is low, is below a half, the optimal price is high. So we have a premium downstream market because we want to charge a high price. If mu bar is above a half, above the prior, the optimal price under the prior is VL. So we have a mass downstream market. So at the prior, if the prior is above mu bar, we want to be committing to the high price in the future. And if the prior is low, we want to commit to charge the low price in the future. And that is actually an interesting case, because if I'm selling to sometimes high quality vehicles today, I would still want to commit to charge the low price to make it more profits from the examiner perspective. So suppose we have full commitment. Now we're doing sort of the Garrett Pavan or Toyka Pavan, whatever. Pavan, Siegel, Toyka method. Now we have a dynamic mechanism design problem where we can use a Pavan, Toyka, Siegel, Toyka econometrica to show that the mechanism there is direct mechanism. The first period types are theta. The second period type has to report theta and V. So the second period probability of trade and the second period transfer depend on, the whole vector of types. And subject to truth telling and participation. And the upstream virtual values are given by this because we have assumed positive density. So now the solution of this problem, I'm not going to discuss it too much, is the product line is the same as Musa-Rosen. So it's a maximum of 0 or the virtual value of some type divided by C. That's Musa-Rosen at 78. And the second period, the pricing, no, this is commitment. Now, there is commitment from the ex ante, and the commitment solution to this dynamic problem is as follows. We're going to be selling, when the reports are theta and VH, the consumers are going to be getting the good. If the reports are theta and VL, the consumer is going to be getting the good only if the theta is above a value theta star, and theta star is this is a number that corresponds to this expression. F1 of theta star is a max of 0, and this expression minus gamma. So if mu bar is above a half, this thing is negative. This thing is negative, so the max is always 0. So when mu bar is above a half, there is no period to price discrimination because we are selling to both types, VL and VH. We're selling to everybody, no matter what is the theta and what is their V. So that's the commitment solution. So, so here the lessons are the product line is identical to the case without downstream interaction. We have no further distortion in the product line. And then we have reverse price discrimination in the second period. Lower types face a higher downstream prices. So we have a quality discount like in the airlines where they give you access to free access to the lounge. So the downstream service is the lounge. And if you're a high value customer, you get for free in the lounge. And if you're a low value customer, you don't get to the lounge or you have to pay. So that's the commitment. That's not our work. That's basically the more vanilla part of the work. Now, I'm writing now what happens as a function of the gamma, depending on the mu as well. And now let's go to the thing we want to talk about more interesting, which is how we use our revelation principle to write down the case under limited commitment. Again, we're going to start with our mechanisms. Let me remind you, communication is direct, messages are beliefs, equilibrium is truthful, and output messages coincide with downstream firms' equilibrium beliefs. So this is our mechanism. So we know what's going to happen in the second period of the sequential rationality. We're going to sell at VL for this posterior, sell at VH at the high posteriors. So let Q star VL of F2 denote the downstream firm's decision to serve the low types. We are always serving the high types. So the question is, so remember, the second period mechanism is we're going to be either charging the low price or the high price. When we sell at the high price, we're only serving the high types. So the question is, when do we serve both types? That's basically what we are trying to summarize here. So we're going to be serving both types if the posterior is below mu bar, which means we will ask the low price. And posterior P bar equal to mu bar, where we are indifferent between any number here or any price. And we are going to be serving only the high types, so no serving the low types if the posterior is above mu bar. So the die breaking here is crucial. This is really what is going to drive the product line design. So to give you some intuition, when under commitment, the firm wants to be charging the low price in the second period, the firm is going to bunch a bunch of types to a posterior. It's going to offer them, it's going to flatten. Instead of like Musa Rosen is a fully separating menu, if you remember. So every type is getting a different quality, but it's basically sort of you are distorting the bottom. So after you exclude some types, you start fully separate. You start fully separating menu, and of course everyone is getting a distorted level of quality compared to the first best. But there is a continuum of quality. What we're going to be seeing here, we're going to be bunching types in one belief, so that we can arrive at this belief with a lot of probability to commit to the price we wanted ideally to put from the beginning. So sometimes we will actually be sacrificing. We're going to be separating, we're going to be excluding, separating, bunching, separating. So we're going to be having these kind of more crazy menus. Like we are going to be bunching types in the middle and separating types below them and above them at the optimal. So that's all we're going to see happening. So that's why this belief is going to be crucial. It's going to be all the game for the first period seller. This is like your joker. When you have a belief, when you have multiplicity, it's awesome, because that's where you can leverage to create different types of, you can use that to break things the way you want. And in information design, we were usually doing the center optimal, the same way we do in information design as we do the center optimal continuation. We're going to be doing something similar here. And if we have a game with an infinite horizon, there's more things we could potentially do, but we haven't explored those things. All right. So the profit maximizing mechanism solves the transfer in period one as a function of the posterior minus the cost of the quality chosen as a function of the posterior plus the probability we're serving the low types at the induced posterior times VL plus the probability we're serving the high types at times VH. And then we have to integrate overall posteriors. Now we have integrals, and that's because we have a continuum, and now we're choosing the max. We are maximizing the we're choosing the continuations here as a function of posteriors possibly, and Q1, X1 as before, and beta. So we have, as usual, our participation, truth-telling, and base consistency constraints, the same way we did it for the two-period problem. Now, we're going to do steps to simplify. First, the first step we do when we have transfers is we use the incentive compatibility and in envelope characterization of consumers' payoff. This is the thing we always do in mechanism design when we have transfers, right? Either under commitment or limited commitment. Sorry. The second step is Bayesian plausibility. We're going to replace the beta by the induced distribution of a posterior tau. And now the objective function eventually will depend only on Q and tau, as we did with the two types. So now you see all the hard work we did for the Dinky 2x2 model. You can see the economics showing up here. And of course, the fact that we have a dinky continuation problem is a simplification here just to get an analytical solution. More generally, you would have some more complicated continuation. And then we're going to drop the monotonicity constraints that come up from incentive compatibility and going to solve a relaxed problem as we usually do and verify it satisfies. That's usually what we do in mechanism design. So now there is a primitive force driving the product gap. Quality must compensate the cost of price discrimination. So we're going to substitute higher prices tomorrow for higher qualities today. And this requires higher types to sort into higher quality. So if we want to sustain high prices tomorrow, we have to distort types into higher qualities. And we're going to see when the sellers, we showed this holds when the firm offers a menu. So each type is going to be mapped to one posterior and hence to one quality and X pair. And under assumption 2, the optimal mechanism will actually be a menu. And so maybe these comments were not so useful. But in any case, we're going to show that eventually the problem solves the optimal mechanism can be implemented with a menu. So let's go to see how it works. So suppose an incentive compatible mechanism is a menu. So that's going to be without loss of general support. Then downstream will extract quality. So consumers who get the same quality face the same downstream price. And downstream prices are monotone in qualities. So higher qualities command higher prices because higher types sort into higher qualities. And if the menu induces price discrimination, there must be a product line gap. Why? Because if Q1 is followed by VL and Q1 prime is followed by VH. So if we have, now I'm trying to build an intuition of why we get this kind of coarse menu. If we have two different varieties offered, followed by different prices, this price is gives rents in the second period. This price does not give rents. So the types who are sorting into this variety today, they're basically being compensated for the rents they're losing tomorrow. So the quality differential today must be substantial for you to sort to the higher quality because you're losing all the rents tomorrow. That's what I'm trying to say here. So in particular, the quality, you get Q1 prime must be above Q1 plus some gap, necessarily gap, the change, the difference in the rents. So that kind of gives you the gap that we need in quality, the difference in each variety, the difference in qualities that are offered by different prices has to have a discrete jump. And that creates this coarseness. So Musa-Rosen offers you a continuum. When you're served, you're offered a continuum of qualities. Here, this is not going to be necessarily the case because unless the qualities are offered followed by the same price, then you're fine. But if you have different qualities offered by different prices, which is what happens here, higher qualities track higher thetas, so you want to charge the high price. Lower qualities track lower thetas, you want to charge the low. That creates the gap. So that's a very intuitive thing that you could even get without the direct Blackwell mechanism. That's what I'm trying to communicate. Here's some economics that you can communicate to an undergraduate class.
So is this similar to the classical contract theory paper you mentioned in the previous lecture? Two-period model, impossibility of full separation in the first period.
Yes, this idea, roughly speaking, this is sort of the idea that if you fully separate today, you need to be, yes, so if types that fully separate forgo all information rents, and that's the idea that also underlies the idea of impossibility of separation. Excellent, yes, you are like all way ahead of every, yeah, it's true. This is really the problem of separation.
Okay.
Exactly. Thank you for making this a very good comment. Okay. So now let's think about how we write down the virtual surplus. So in the relaxed problem, we're going to choose a mapping from beliefs. So now let's go back to mechanisms. Forget about the menus. This was just an intermission to get some economic intuition that you can give you even to like undergraduate students. So now let's go back to designing Blackwell mechanisms. We are going to choose an allocation rule as a function of beliefs to qualities and base plausible distribution to maximize the virtual surplus today, which depends on Q and F2, and the virtual surplus tomorrow, which is the dynamic rent and depends on how informative theta is about V, times the tau, a distribution over posteriors. And we're ignoring monotonicity. We're going to point-wise maximizing Q1, very similar to the way we did in the pictures before. So under these assumptions, so I'm not right. I don't know if I have this expression here, maybe not. Maybe I don't have it. No, I don't have it. Sorry. Now how do I go back? Great. Now I have to go back to all this stuff. Oh no. Sorry. Sorry, I don't have these expressions, but they are a bit of a mess, but you know, they're analogous to the virtual value expressions you have. Is there an easier way to go back? Maybe this one here. All right. Almost there. Sorry about this. Okay, so we're writing this expression in terms of virtual surplus. And okay, so under these parametric assumptions, the objective function is a function of the posterior mean mu F2. So this is what all these parametric assumptions buy us, and then we can rely on Forczak and Martini and Ariel and all to solve the problem. Because otherwise, if we don't have these parametric assumptions, the objective function is going to depend on the entire shape of the posterior, and we don't have information design tools for those. I'm out of time, but can I take like 5 more minutes? I mean, it's for you, not for me. It's up to you.
It's fine. Yeah. And,
No, please tell me. Should I stop?
Please go.
Please go.
Okay.
Unfortunately, I have another class to study.
Okay. Yeah, please, if you have to teach, I'm so sorry. So sorry for going over time. So okay, so let me just quickly summarize. We solve this problem for different priors that are above mu bar and below mu bar. And depending on that determines on what price you want to charge. So for example, if you want to charge the commitment price is high, that introduces different distortions than if the commitment price is low. So let me try to show you what happens. So suppose we are in the case where we are in the premium market, so the prior is above mu bar, so we want to sustain a high price. What we are going to do at the optimum when we solve the problem is we're going to exclude a larger range of types. So this blue, the black line is the first best. The second best is the blue. We exclude some consumers and then we fully separate. The red is limited commitment. Limited commitment is going to pool all of those bottom types to induce a posterior exactly at mu bar. At mu bar, the seller is indifferent between asking the low and the high price. So we're going to specify the high price, and we're going to be fully separating those consumers and asking them the high maintenance price. And we're going to be excluding more. So here we see more distortion compared to second best because we exclude more consumers. Another case is when we have mass market. So we want to sustain the low price. So now we actually offer a very coarse product line. We exclude types and we offer only one single variety, a single variety. That variety is designed so that we sustain the low, we induce the posterior at mu bar. So we design that posterior. At that posterior, we're charging the low price. And now we have left with a two-tier product line. Very coarse. So in other cases, we do this case where this is when we have, again, we want to charge the low price and we do, what we do is we exclude, we fully separate, we pull in the middle, and we fully separate. And this pooling here happens so we can sustain the low price as much as possible, but we do have some consumers buying at the high price. But all of these consumers, these consumers that are excluded, but all of them are charging the low price. These guys are facing different varieties and the low price, this single variety bundled here and the low price, and then fully separation. So the welfare actually is ambiguous. In some cases, the consumer is better or worse. And given that I have to wrap up, let me just say that this optimal mechanism can be implemented by a menu. So we have a simple implementation. And we also have a privacy extension in the paper. So we think about someone who sells the data. Let me not tell you, I've kind of taken you, the main takeaway is that better match value trades off, gives you more possibilities for price discrimination. And this analysis highlights the homogeneity of the products offered to consumers. And it kind of speaks to the current debate about privacy, but you can think about similar things happening for job design in organizations, incentives and so forth in teams. Well, if you have more than one agent, but we don't have yet. So, we think potentially relevant where we have procurement auctions, so learning about the efficiency of producers, organizational economics, designing tasks to learn about workers' abilities. So these are kind of similar problems. And let me just talk about the road ahead. As you see now, we have some language. It speaks to a particular class of games, not all games. You can think about mechanisms with memory, as we said at the beginning of the lecture. But now the key is that we know very little about how optimal mechanisms change with principles information. We don't do a lot of comparative studies of how the mechanisms change with distributions. And we need those results to be able to think about richer problems here. And we also know very little about optimal information structures, especially for continuum of types. So there are a lot of you are students here. There's a lot of work that needs to be done, both in information design to think about how we design information design when we care about the whole shape of the distribution, but also how optimal mechanisms change as we change the shape of distributions. And those types of tools will actually make progress to maybe more interesting mechanism selection problems, either with limited commitment or other types of mechanism selection games. So I think that's all I wanted to say. And thank you for bearing with me for a few extra minutes.